Let us revise KCSE questions on radioactivity. And I want to tell you this, we are going to start out strong with an application on radioactivity from KCSE 2021. So the question goes as such. Figure 5 shows a part of a radioactive decay series. Write a nuclear equation for the formation of nuclide K from nuclide X. So we are supposed to be getting our information from the graph. Curly, right? Okay, now let's start. So our parent nuclide in this case is X. So X undergoes decay to form Y. Y undergoes further decay to form Z until finally Z undergoes decay to form K. So we're being asked for a nuclear equation that summarizes the whole of this starting from X to K. Now we cannot go straight away to it. We have to go systematically. So what you're going to do is we are going to write our final equation, although it's going to be just a skeleton because we don't have the information yet to fill it in. So we are going to start with X, which is our original parent nuclide. X has the atomic number of 83 and the mass number of 213. So it's going to be on that side of the equation. We're going to draw an arrow, drop K there. Why? Because the question is asking us that. So K, from the graph, we can clearly see that K has the atomic number of 83 and the mass number of 209. Now, we don't know whether it's alpha particles or beta particles that are being released. We're not going to take into account gamma rays at this point because gamma rays have no effect whatsoever on the mass number and atomic number. And whatever particles we are having here are clearly changing these two. Now, if we look at the atomic number has remained the same. We are still at 83 for both X and K, surprising, right? Because we can clearly see the atomic number changing as decay occurs from X to K. So it changes and then goes back to where it was at the beginning. Now, if you look at the mass number, this has clearly decreased by 4. Now, alpha particles cause a decrease in both atomic and mass number. So they decrease the atomic number by 2 and the mass number by 4. Beta particles increase the atomic number by 1 but have no effect on the mass numbers. So clearly these two don't just match with the information that we have. So what happens is we probably have a mix of beta and alpha particles being released. So finally we get what we have with K. So let's go systematically starting from X. So X undergoes radioactivity leading to formation of Y. Now let's look at Y. Y has the atomic number of 84, same mass number as X. So this is beta radiation. A beta particle was released. Why am I talking about this? Because when you have beta radiation, a neutron is converted to a proton. Therefore, you have an additional proton being present. But because it's simply a neutron converting to a proton, the mass number remains the same because the mass number is the sum of protons and neutrons. So that is our nuclear equation for step 1. Now moving on to the next step. What happened between Y leading to the formation of Z? So Y undergoes radioactivity leading to Z, which has the atomic number of 82 and the mass number of 209. So we are clearly having a decrease in the atomic number by 2 and a decrease of the mass number by 4. This, my dear students, is an alpha particle that was released. Our last one, Z to K. So if we look at Z, that is Z, and K, that is K. So what is the difference between the two? We have an increase in the atomic number, mass number remains the same. This is beta radiation. So in short, the changes that are seen leading to the formation of K from X involve the release of 2 beta particles and 1 alpha particle. So how do we sum all of this up in our nuclear equation as such? Those are the symbols that are used to represent the alpha and beta particles. In case of the beta particles, we have the number 2 to symbolize that 2 beta particles were released through the decay series. So this brings us to the end of this lesson. I'll be tackling more revision questions in the next part. See you there.